So a lot of us are getting into reactions, so let's talk a little bit about redox reactions. So redox is an abbreviation that stands for reduction and oxidation. And so a reduction oxidation reaction we call a redox reaction. And it's a little bit special because in a redox reaction, we actually have a transfer of electrons between two species, okay? And so when we have that gain of electrons by one species, that species is being reduced, and then the species that's losing electrons is being oxidized. And it's important to remember that if you have one, you must have the other. These processes go hand in hand. So then the next question is, how do we tell if a reaction is a redox reaction? So you do that by assigning oxidation numbers. So let's take a closer look at that. Okay, so remember what I just said. Oxidation is loss, reduction is gain. And you can remember that with this little mnemonic oil rig. And we're talking about electrons here. So something that's being oxidized is a species that's losing electrons, and a substance that's being reduced is gaining electrons. So important to remember that the electron is negative. So when you lose electrons, you become more positive, and when you gain electrons, you become more negative. So then how do we tell what's going on? And the answer to that is you assign oxidation numbers, and there's rules for doing that. So this is a little table, and it's important to remember as well that you assign these in order. And you kind of just need to memorize this. But memorizing this is not hard because most of this is going to be numbers that you've already been exposed to because we think of them as charges in a lot of cases before we start thinking about redox. So here we go. So first of all, if you have an element in its elemental form, the oxidation number of that species is going to be 0. And you need to make sure that you're also watching out for diatomics. Okay, remember that rule of 7. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen all exist in diatomic form. After that, if you have a monatomic ion in the reaction, the charge of that monatomic ion is its oxidation number. So those are equal. Group 1A, the first column of the periodic table, is +1. Group 2A, second column of the periodic table, is +2. Then comes hydrogen. Hydrogen is usually +1. Now there's a major exception to that. If it's bonded with a metal, then hydrogen is -1. And then finally, oxygen is -2 most of the time. Not always, but most of the time. So now that we know about oxidation numbers, how do we tie them together? And the other thing to keep in mind is we have more elements besides just these. If you have these memorized, you're going to be able to figure out pretty much everything else by keeping in mind that the sum of the oxidation numbers within a species equals the charge of the species overall. So let me show you some examples of that. So we're going to assign oxidation numbers to each atom that's present in each compound here individually. So let's apply our rules. So first of all, we do have an element in its elemental form, and that's oxygen. Remember, it's diatomic. So the oxidation number of oxygen here is going to be 0. Now I'm just going to go through. So I have CH4. I don't know the C based on the rules I memorized, but I can see that hydrogen here is combined with a nonmetal, and so that means that the hydrogen oxidation number is going to be +1. Because there are 4 of them, that gives us an overall charge of +4, but this compound is neutral. So all of that must be canceled out, and so that means in this case that carbon is going to be -4. Now let's go down to carbon dioxide. Down here I have oxygen, which is going to have an oxidation number of -2. I have 2 of those, so I'm going to multiply that by 2, and so I've got -4. Again, neutral compound, so in this case, carbon is going to be +4. And then if I look at water, my hydrogen is combined with a nonmetal, so it's going to have an oxidation number of +1, and then we also expect oxygen to be -2, which we can also see if we multiply that by 2. They cancel out. So that's our oxidation numbers for the individual atoms in each species. Now, maybe you've already recognized what I'm doing here. This is the combustion of methane. Now, this equation is not balanced. I need to put a 2 in front of that and a 2 in front of that. But one reason I went ahead and did oxidation numbers before I showed you the whole reaction was to show you that the coefficients do not impact oxidation numbers. Now, we can use these oxidation numbers to determine what is being oxidized and what is being reduced. if anything. So first of all, if nothing is being oxidized or reduced, this is not a redox reaction. So in that case, all of your oxidation numbers for the species would stay the same from reactants to products. But that is not what we have here. So we have oxygen that's changing from 0 to -2, and we have carbon that's changing from -4 to +4. So because oxygen is going from 0 to -2, it is being reduced. And because carbon is going from -4 to +4, it is being oxidized. Okay, and that's it. That's how you apply oxidation numbers to justify redox reactions.